Hello and welcome to this first class. So we are going to be starting with section 2.1, and when we're talking about tangent and velocity problems. Alright, so our first question, or our first thing we want to understand is how to find the tangent of some particular function. So what I mean by this is if we take some particular function like this, call this function f, suppose we want to find the tangent line to our function f at some particular point. So this could be a point x, and we might want to find, actually let us call it a and not x. We might want to find the tangent line that goes through this point right here, which has got coordinates a, f of a, that has the same slope as the graph of the function at that point. So it's going to look something like this. Okay, that's finding a tangent line. So finding a, and tangent line is going to be abbreviated to T line from this point onwards. Okay, so that is the first problem. I'm going to do a specific case, which is just considering a quadratic function. So suppose we have f of x is equal to x squared, and let's take the point 1, 1, because when x equals 1, we're going through the point 1, right? So let's draw another picture. Looks like this. Here we are at 1, 1. Okay. And we're going to try and find the tangent line that goes through this point. Okay. So a tangent line is a linear function, right? So linear function, which in calculus means it's going to have this form. It's going to be ax plus b, right? And what does that look like? So it has an intercept here at b, and this number a gives its slope, right? So a linear function will look something like this. So to define this linear function, we need two things. We just need to find the a and the b, right? And the harder thing to find is the slope, right? So we're going to first focus on that. And the way we're going to try and do this is we're going to look very closely at this graph of this function, and we're going to say, okay, here we are at this point. This is the point P. Let me call that P on the picture. So this is the point P, 1, 1. And if we move up the graph a little bit to another point here, call that point Q, this is point Q, then if we consider just a little line segment that connects P to Q, like this, you can see that that line segment has got a slope which is somewhat like the slope that we're looking for, right? So what is the coordinates of our point Q? So if Q lives here above this point x, this is 1, x is a little bit further along, then Q is going to have coordinates x squared. No? Cool. So we end up considering a little kind of triangle. So this picture is getting small, so I'm going to blow it up in a second. So we're going to do a lot of this stuff. So we have a little picture here. We'd like to see what happens. We'd have a bigger blow up of what happens. So imagine you have a microscope which takes this picture inside this circle and blows it up to a bigger scale like this. Okay. What do we see? We have P over here, and we have Q over here. So Q is x squared. This is P, which has got coordinates 1, 1. Okay. And the tangent line is something over here, and what we have is like the graph of the function kind of doing this. Right? But we're just going to try and focus on finding the slope of the line that goes through PQ for the time being. Okay, so what are we going to do? We're just going to draw a triangle, okay? And then we have to consider this distance and this distance, okay? So what is the vertical distance? Well, the y coordinate of q is x squared, the y coordinate of p is 1, so this thing will have to be x squared minus 1, right? And what about this thing over here? Well, the x coordinate of q is x, and the x coordinate of p is 1, so put that over here. So this will just be the distance x minus 1. Or maybe I should just put it here. This is x minus 1. Yeah? So the slope is how far up or down we go divided by how far along we go. Yeah? So that is easy to do now. So we're running out of space. Let's stick it in here. So MPQ is the slope of line segment PQ. So this is the notation for a line segment, okay? And we can just calculate what it is. Let's put it over here. So MPQ, given by this, is going to be x squared minus 1 over x minus 1. Cool. So we can do some algebra. We can expand that out. X squared minus 1 is going to be x minus 1, x plus 1. So long as x is non-zero, that's just going to give us x plus 1. Yeah? If x is non-zero, if x minus 1 is not equal to 0. Cool. So that thing gives us some kind of idea what is the slope of this line segment. In fact, it gives us the exact expression for it. And the reason it's relevant is that we can see from this picture that this slope is a bit like this slope. And actually we can make it look more and more like the slope of the tangent line that we're looking for simply by taking x closer and closer to 1. Right? You can just see that from the picture. Right? So if I put it on the blown up picture, if we draw the tangent line that we're looking for, it's like a line like this. Yeah? And as we let x get closer and closer to 1, then this line segment has a slope closer and closer to this line segment, which is the one that we're looking for. I'm going to try and put this in a different color. No, not going to make a difference. Yeah? So, if that's not clear to you, just spend a few seconds looking at it. Convince yourself that as x gets closer to 1, then this slope gets closer to this slope. Yeah? Once you're sure about this, then what we're about to do is going to make sense. We're going to try and find out what this slope is, or the slope of the tangent line at 1 is, simply by plugging in numbers, x closer and closer to 1, and putting them into this formula. We're going to make a table of values and see what we get out from that. Okay, so I have to erase the board, and we'll continue this when I've got the board clean. Okay, so let's draw a little picture here just to remind ourselves what we're trying to do. We have this quadratic function. We're trying to find the tangent line at the point 1, 1. Okay, so this is the point 1, 1. And we are doing this by considering the point q x squared and figuring out the slope of the line segment that connects P to Q. Yeah? And we denote that slope by P or MPQ, and we did a bit of algebra and it turned out to be x plus 1. Yeah? And so this here is 1 and x is a little bit ahead of it. Okay, so we're gonna do some just numerical investigations. So let's just create a table. So let's put x over here, and let's put the slope MPQ here. And if we put x is 1.1, I'm sure we can just read it off, it is 2.1. If we put 1.01, then it is 2.01. 1.001, then it's 2.001, right? And it looks more and more like we have that the slope of this line segment is tending towards 2 as x tends towards 1, right? Which gives us the strong impression that we have that the slope of the tangent line is 2. So let's write that down. So it seems the slope of t line is 2. Okay. We don't know this for sure because we're just doing this thing and it looks pretty convincing, but later we'll be able to say more in a more definitive way that this is actually correct. Okay. So now that we know the slope, we just need to find the equation of the tangent line. So the tangent line has to have this formula, t of x, and it's going to be a linear function, so it's ax plus b, but we know the slope is 2, so it's going to be 2x plus b for some b. Right? And we have to find the correct b so that it actually goes through the point 1, 1, because that's the other thing it has to satisfy. And then there's a kind of simple formula you can just apply. So look at this. If we write t of x is 2 of x minus 1 plus 1, that's the same as 2x minus 1. And if we stick in x equals 1, then this part here vanishes and we get 1 out, right? So we get t of 1 is just 1. So this thing definitely is of the correct form. It has the right slope, and it's going through the right point. Yeah? And you might have seen this in high school as being called something like the slope intercept, I don't know, like xy form. You see it like this, like x minus 1 is 2 of x minus 1. And this is how far we are changing in the y, and this is how far we're changing in the x, and this is the slope. Yeah? You might have seen that. But it's exactly the same as this. Yeah? So that's the answer to our question. We've found exactly what the tangent line is. Yeah? So this thing is our answer. Cool. All right. Now we're going to talk about something that seems completely different. We're going to make what seems like a discontinuous jump, and we're going to talk about velocity. So, Galileo discovered this remarkable formula that if you stand on top of some building and you drop a stone or a shoe or a rock or a plate, if you drop any normal object, it's going to obviously fall down. And if t is the number of seconds after you let it go, then the distance it falls is given by this particular formula. S of t is 4.9 times t squared meters. Okay. And there's a reason for this, where gravity is fairly constant near the surface of the planet. So this is a universal law, which at the time was a big surprise to people, because it was the very beginnings of modern science, and the idea that you could do something and then predict exactly what's going to happen in the future was at the time astonishing. It just wasn't available before then. But this is exactly what this tool gives you. It says you do something, you drop a stone, a shoe, a rock, whatever, and you know exactly where it's going to be in the future at whatever time you want until it hits the ground, because it's just obeying this particular law, which is routine for us now. But it's the embryonic beginnings of modern science, of describing the world with the language of maths and having this predictive power as a consequence, this predictive power that allows us to build everything that we use in our modern life. If we didn't have this, we were just purely trying to develop modern society and technology with just experiments, but without any idea which experiments were worth doing, which attempts to build something were likely to succeed, then it would not get anywhere. It would just be ridiculous. We couldn't possibly succeed in building the very sophisticated things that we require and use daily if we didn't have any theory, if we just tried to just stick things together and hope that they work, right? So the whole story, the whole transformation of society kind of begins around here, at least with respect to science. So this is Galileo's formula, and we're going to use this to answer a specific question. So I'm going to formulate the same question as in the book, which is as follows. So, question. Suppose a stone, is dropped. So in the book they say the CN tower, which is a very tall tower, but we don't care, is dropped from tower how fast is it falling after 5 seconds? Okay, so how would we try and answer this question? Well, what could we possibly do? Here's what we could perhaps do. Let's draw a picture of the CN tower, and we are dropping our stone. Okay, so here we are. It's not like our other picture. It's meant to be a little man. It's dropping the stone. Okay, and suppose we are here at 5 seconds. So that's S of 5. Exactly 5 seconds after we've dropped it, the stone is here. Right. So if we consider where it is after 5.1 seconds, then it's going to be S of 5.1. And that'll be somewhere here. Right? So this thing here will be how far it travels in that time interval from 5 to 5.1 seconds, right? Which is 0.1 seconds. Yeah? So if we look at this, if we write S of 5.1 minus S of 5 over 0.1, that is not the velocity, but that is the average velocity over this time interval. Okay? And that might make a reasonable approximation to the velocity. Yeah? But not necessarily a particularly good one. If we change the game a little bit, and instead of fixing the time interval, let's just fix positions. So let's try a different kind of mental experiment. So imagine we're trying to consider or find out how fast the car is going. So the car is going along the road like this, okay, and we put a sensor right here. So this is the sensor here at A, and then the car's going like this, a sensor here at B, and then we record the time it passes A, and we record the time it passes B, right? And we set it up, we know the distance between the two, and then we'll know how long it takes to go from A to B. Yeah? So then we can take this distance from A to B and divide by how long it took to go from A to B, and that gives us the average velocity from position A to position B, right? But that's not necessarily the same thing as velocity. You can imagine that the car is going incredibly fast as it passes A, and then the driver jams on the brakes, right? And then it slows dramatically and then crawls forward until it crosses B. So it could be crossing A at 100 miles an hour, and then just after jams on the brakes, and then from here to here, it's going at 2 miles an hour. Yeah? Then the average would be, I don't know, 20 miles an hour. But that's nothing like the actual velocity at time A. Yeah? So how could you try and do a better job? Well, you could just put this sensor closer. Instead of doing from A to B, let's do it from A to C, where C is like this. Yeah? And that seems like it would do a better job, because even if the driver jams on the brakes, it can't decelerate too fast. So it's more likely that the average over this little interval from A to C is like the actual velocity at A. Yeah, but what if it was not a car, it was a motorcycle, and it's very good braking power, decelerates much faster than a car, you can still get a completely false answer, right? This will still not really give you the velocity at time A. Okay, well, you say, let's just put a sensor here at D, get a very precise sensor here at D. But you can still imagine a scenario where this fails. You could have a rocket, right, which passes A and then thrusters fire in the opposite direction and dramatically slow it down, and we still don't get a good answer. But we're getting a more likely a better answer, right? More likely getting a better answer as we get closer and closer and closer. But to actually get the real answer, we can't just be satisfied with sticking these things quite close together. That's not actually the velocity at that instant. It is, the best we can do is say it's the average velocity over a tiny, tiny interval. Yeah? And that's in physical space where we set up the sensors like this, right? Where we consider the interval over a physical interval of points. Let me say that again, where we consider the average velocity over a physical interval of points. Here we're considering the average velocity over a time interval. Yeah? Here we're considering the time interval because we're letting it drop by some certain amount of time and we're seeing how far it travels, as opposed to here the distance is fixed and we're seeing how long it takes to cross this distance. Yeah? Here we are fixing a small time interval and we're seeing how far it travels over it. So it's a different game. Yeah? But we still have the impression that we're going to get a better answer if we let the time interval get smaller and smaller. Yeah? So let's write that down. So average velocity, over time interval, I'm going to just write it like this, 5 to 5.1. What's that going to be? It's going to be s of 5.1 minus s of 5 over 0.1. Okay? So, to get some kind of reasonably decent answer, we are going to create a table of values as we allow our time interval to get smaller and smaller and smaller. And then we're going to see what that looks like after I clean the board. Let's create our table of values. And maybe it's just going to save a bit of time if we also do some algebra first. So what do we have? We have that s of t is 4.9 times t squared, right? And what if we do this? So the average velocity over time interval to 5 plus h. Now h is just some small number. So previously we took h to be 0.1, but let's just not define it. Let's just say it's h and it's some very small number. What's that going to be? It's going to be given by s of 5 plus h minus s of 5 over h. And then we can just see what that comes out. So it's going to be 4.9. And then we're going to have 5 plus h squared minus 25, because we have 5 squared over h. Right? And then we expand that out. We're going to have a 25. We're going to have a 10 times h, and we're going to have a h squared. So this is going to be 4.9. And we're going to have 10h plus h squared over h. And so long as h is non-zero, we can cancel a h, so let's do that. So it's going to be 4.9 times 10 plus h. Yeah? So if we do a table of values, so this is the time interval. And this will be the average velocity, so I'm going to write a v. And if we do 5 to 5.1, that's the same as taking h to just be 0.1, right? So what's this? This will be 49 plus 4.9 times h. Looks like I do need this. So here we're going to have, 49.49. And if we do 5 to 0, to 5.01, we're going to have 49.049. And if we do this 0.001, we have this 49.0049, which you can see from just plugging in the h directly into this. Yeah? Cool. So it looks like as we take smaller and smaller time intervals, we're tending towards the velocity 49 meters per second. And even if we don't even do this, if we just look at this, as h gets smaller and smaller, then this part's going to get less and less important. So it just seems reasonable to us, right? So looks like the velocity. Now I'm going to write instantaneous velocity just to underline that this is a thing that we've taken by taking the limit of having smaller and smaller average velocities over a time interval. Okay, so I hope it's spelled this way. I don't think it's spelled this way. So I have to confess that I do not know how to spell words in any language, but certainly not in English. But I have an excuse. This is not my native language. All right, so instantaneous velocity is 49 meters per second. Okay, cool. Now, what should be coming to mind now is that this building of a table, looking at things on a smaller and smaller scale, is very much like what we did before when we considered the problem of finding the tangent line to the graph of a function. Right? So, what's the connection? The connection is as follows. So, just consider this function s of t, which is 4.9 times t squared, on this axis. So let's just put t going down like this. This is time, and then s of t up like this. Then what do we have? We have a nice quadratic function, right? And when we consider this little part here, 5 to 5.1, and we join up, and it's not quite here, correct that. And then we consider the slope of these points, so this will be p of 4.9 times 5 squared, and then this will be q of 5.1, 4.9 times 5.1 squared. Okay, if we consider the slope of this, that's exactly what we've been looking at before, right? So that's exactly s of 5.1 minus s of 5.1, which is the average velocity over the time interval 5.1 to 5. So we see that what we're actually doing when we do this procedure is we're finding the slope of the graph of the function at this particular point given by time is equal to 5. Yeah. So what we've actually learned is that the problem of finding the instantaneous velocity of this function s is the same as finding the slope of the tangent line at some particular point. And if you think about this a bit more, then this function s, you'll notice it's just the distance away from the top where we dropped the stone. In other words, it's just the displacement or the position of our stone. Yeah? So this is something you've probably encountered, or at least. Okay, so this is where I discovered that the last 10 minutes of what I was saying wasn't recorded because the microphone died because of battery problems. So let me say the stuff again. So what have we learned? We have learned that this thing right here is exactly the same procedure we did before when we're trying to find the tangent line of our function s, our function x squared, right? Which therefore teaches us that finding the tangent line of the position function is the same as finding the velocity. Okay, so why do we do this? Why do we start the calculus course with this particular example? Well, this is the reason. In order to get a precise answer of what the absolute slope of the function was at a particular point, or to get a precise answer of what the velocity was at some instant in time, we had to do this thing of creating this table and then taking smaller and smaller values, right? We had to see how this looked as we passed to the limit, where we have in the limit an interval of time which has got 0 length, right? This is an interval with very, very small length, just from 5 to 5.001. But to actually have the real answer, we can't have any length at all. It has to be a zero length time interval, because that's what instantaneous velocity means, right? And to do that, to make that a meaningful concept, we need the concept of limit, right? And when you first see limits, it can seem like a lot of discussion about not very much, but it's absolutely crucial. We can't meaningfully do these things without it. For example, the concept of velocity isn't meaningful without the concept of limit. You just can't give a meaning to it. If you try to build a device to record velocity, right, what would you be doing? You'd be putting a sensor here and a sensor here, and recording, just as I showed up there, recording the time when the car passes the first sensor and the time it passes the second, and then taking that distance, dividing by the time as your average velocity. But it would take anybody just a few minutes of thought to realize that the better way to get an answer is to put these things closer and closer together. But no matter how close you get them together, it's not going to be the absolute velocity at this particular point. It's just going to be an approximation. And to get the absolute velocity, or the instantaneous velocity, we need to have this interval have 0 length, right? So what is kind of a little bit funny for me is that many people who you talk to, if you tell them you're studying calculus or teaching calculus, they'll say, oh, I never understood calculus, I don't like math, I never saw the point of it, my brain doesn't work that way. And that's completely false. Anybody who has the concept of velocity, who's comfortable with the concept of velocity, is, whether they like it or not, doing calculus. They are actually differentiating a function, they are taking the derivative of the position, and they are using the concept of limit. Our brains are equipped with this facility. We couldn't be comfortable with the concept of velocity otherwise, and everybody is, right? So it's not the case that this is some exotic thing that just some very small number of specialized people need to care about. This is part of ordinary life, just ordinary life, and the ordinary understanding of the world around us requires these concepts. And even if you resist this and think you know nothing about it, you are using these concepts anyway. They're already there in your brain, in your understanding. You just don't have this language to formalize that. Right? But once you do start to develop this kind of language to formalize it, then you can get a much better understanding of the world. And that's what you're going to find out as you proceed down this journey. Okay, so the whole point of section 2.1 was to motivate this concept of limit, which will be discussed in 2.2. Now, how should we start talking about limits? We're going to start talking about limits in terms of functions being close to some particular value L as x gets closer and closer to some particular value A. And the first thing to notice is that we're not going to care about the actual value of the function at A. So that's not going to be part of the definition of limit. But we are going to care about values of x which are very close to A but not equal to A itself. And we're going to write this as the limit. And what does it mean? It means the following. It means we can guarantee that the function f gets arbitrarily close to the number L as we choose x to be inside a very small neighborhood of A that we have the right to choose. So if we take L and we draw this kind of thickness around it, which is just drawn here, so this is our number L, and we put a little thin strip around it, which is just already drawn, then this thing informally means we can guarantee that our function f is going to live inside this strip so long as we're allowed to restrict the values of x to be within this tiny neighborhood around A. And it doesn't matter how small that is. We have the right to choose it to be as small as we like. So here's a metaphor that I like to use to explain this. Imagine that you are tasked with finding the total weight capacity of a bridge. And the way you can do this is, and you're later going to find out this is kind of real, or this is absolutely real, is by writing a computer program, which will give you the answer as an approximation, but the approximation gets better and better as you run the program over and over again. And your boss comes to you first of all and he says, I think we need to get it within 5%, but maybe the contract changes later and it's within 2%. So you say, okay, well, I'm going to write this program that's going to get you to within 5% if you run it enough times, and if you run it more times, to get within 2%. But you have to allow me to have as much supercomputer time as I need to get you to within that precision. And he goes, yeah, the budget is not a constraint. You can have as much supercomputer time as you like. I just need you to guarantee me the accuracy that I want, and I'll tell you afterwards. So you write your program, and then he comes in and he goes, okay, it's 5%. So you run your program for whatever, 10 hours, and then you say to him, okay, here's the answer within 5%. He goes, I'm sorry, there's been a change, now it's 2%. And you say, okay, but you promised me I can have as much supercomputer time as I want. And he went, yeah, that's still true. So you okay, well then I can do it. You run your program now for 3 days. After running for 3 days, you get within 2% error. And you go, okay, here it is, here's the answer within 2%. And then your boss goes, oh, I'm sorry, it's now, the situation's changed again, now it has to be within 1%. And you say, okay, but it's going to be more supercomputer time. And he goes, yeah, that's what we agreed, you have as much as you want. Okay, so you run the supercomputer for, whatever, a week to get it within 1% error. Yeah? But he's happy because he asked you to sign a contract to provide him something that gets him within arbitrary error if you have the right to have as much supercomputer time as you want. When you write this, you are signing a contract. You are saying, I guarantee you that I can get you f to within whatever error of L you want, so long as I have the right to choose x to be within this very small neighborhood around A. And that is my choice. It doesn't matter how small I insist it is, that's my choice. if you give me that freedom, I can get you to within that level of precision. Yeah? That's what this means. You are signing a contract. It is not a non-trivial statement. It is a serious thing. It's not enough to be within 0.000000001 of L. You can do it for any error, no matter what. Okay? So if we look up here, what we were trying to do with this table, we were trying to see what would happen as we took smaller and smaller time intervals. So h was the 0.1 in this calculation right here. Huh? And we want to see what happens as h got smaller and smaller and smaller. And we could have just kept doing the calculations, putting in the numbers. But if we look at the algebra over here, it simplifies to this expression right here. And it looks like this thing is getting closer and closer to 49. Yeah? But to say that the limit is 49 would mean that the difference between this and 49 is as small as any error that we want, so long as we're allowed to restrict h to be sufficiently small, close to 0, not equal to 0. Yeah? And that we can see is true, right? No matter how tiny error you want between this number and 49, you can get within that precision by insisting that h is small enough, because the only difference is 4.9 times h, right? So in this particular case, and it's jumping forward a little bit, we could actually show in a precise way that this limit exists. Yeah? So this quantity represents the function as a function of h, and L in this case is 49. Okay? So this is something we could actually show, and that's the kind of thing we're going to be doing going forward. We're going to understand what the limit means, and then we're going to learn how to calculate limits and show precisely things like velocities, slopes are what they actually are. That'll be the power of this. All right, I hope the audio went through this time. That's it for today.